Alright, so in this video we're going to discuss force and torque on a magnetic loop. So this is going to turn out to be very similar to force and torque on an electric loop. However, we do need to deal with the fact that magnetic stuff is a little bit more three-dimensional. Alright, so I have a loop here, so square loop, and so we have a current going through that loop, which gives us our drift velocity. So we do have moving charge, and then we have our magnetic field acting here. So we calculate magnetic force by the equation given here. So we're going to do Q V cross B. Now for sides 1 and 3 here, the drift velocity, which is inside of the current, is parallel to the magnetic field, which means if we do V cross B, we're going to end up with 0 because the angle between them is 0. For side 2, since the current is going down and the magnetic field strength is going to the right, so I'm going to hold my fingers and point them down, and then I'm going to rotate my hand so that I can grab the magnetic field going in the positive X direction. My thumb points out of the board. And on the other side, so side B, now our current is going up. The magnetic field is still going to the right. So now I'm going to point my fingers up, rotate them to grab B, so my thumb would point into the page. So the force is going to be equal but opposite because we have the same charge we're worried about, we have the same drift velocity, and it's in the same magnetic field. So the net force, therefore, is 0. But now we're going to look at this from the torque perspective, and the fact that these forces are equal but opposite mean that we're actually going to cause a rotation because there is a net torque applied. So let's look at that. Alright, so I've redrawn the original picture here with our magnetic field and our current going around. But now I've drawn a top-down view. So we have force 1 coming out, force 2 going in. And because they're both going to cause, so we have a rotation point down through the center here, because they are both going to cause a counterclockwise rotation, because this one is going to pull up and around here, since this is our rotation point, and this is going to pull down and around here, since this is our rotation point. So if we remember from Physics 151, torque is equal to force times the lever arm. Now these are already acting perpendicular in the orientation I have them to the lever arm. So the lever arm is going to be the distance between our rotation point and where the force is applied. So since I labeled this side A, the distance between the center here and the end is going to be A divided by 2. So that's going to be our lever arm over here. And our force, and force 1 and force 2 are going to be equal because they're in the same magnetic field with the same current. And remember, magnetic force for a current carrying conductor is magnetic field strength times the current times the length of wire. So the length of wire that is experiencing the magnetic force is side B. So we're doing BIB, and since all those values are the same, the two forces are equal to each other. So I've subbed up here our net torque. We have a torque from force 1 and a torque from force 2. I've subbed in our force equations, and I've subbed in our lever arms. So that reduces down to the magnetic field strength times the current times the length of the sides multiplied together. And the length of the sides multiplied together is the same thing as the area. The only problem with this equation is that it assumes that the magnetic field and the drift velocity, so the current, are perpendicular to each other. So if we're not in this orientation, so we start rotating, so there is actually something other than a 90-degree angle between the two of them, then we need to use the sine of phi in order to establish what the torque is. So the torque's going to change. It's going to go from its max value to 0. We can also define something called the magnetic moment, which is the current times the area. So we can also calculate the torque by taking the magnetic moment crossed with the magnetic field strength. And just as a side note, we can calculate the potential energy due to this that's stored by taking the negative of the magnetic moment dotted with the magnetic field strength.